to thank the organizers for this very kind invitation. And there were two introductory talks this morning, which were quite helpful to give some background about what I would like to tell you a little bit today. And I'll try to give a presentation by the book in the homeland of Gutenberg. That's the least I can do. So first, I would like to acknowledge the people who've been instrumental in this research and the Orsay group. So there is an ARPES guy, Andrés Santander-Siro, and a postdoc that we had with Marcelo, Cyril Martins. You recognize this face. And this is my PhD student, Oliver. And then there was an association with the Frankfurt group, headed by Roser Valanti, and these are postdoc Harald Jeschke and Michaela Altmaier, who's a PhD student. Now, in the background, not appearing on this slide, I would like to acknowledge, of course, the Geneva group, because for several years now, I've been closely associated with their research and analysis of transport measurements. Now, I'm going to talk today about strontium titanate, hereafter called STO. So if I use this word, you'll know what it means. So that's not exactly what the Geneva group has been pursuing so far, but still you'll see that many of the ideas borrow from them. So just a quick reminder for those who are not familiar with the subject. So essentially what you do is you have a substrate, which is STO, half millimeter, and it has layers, and it's terminated by TiO2, and then on top of it, you deposit by various techniques lanthanum aluminate, and when the termination is LAO, and when the number of layers of LAO lanthanum aluminate short as LAO. When the termination of this lanthanum aluminate is the LAO layer, for 4 or more unit cells, then you find that these two guys, which intrinsically are large band insulators, a gap 3.2 eV for STO and for LAO 5.6 eV, then you realize that you get a conduction at the interface, so a two-dimensional gas, which is fairly confined to the interface, a few nanometers thick, and the electrons which populate it are on the order, I would say, of, in transport, 10 to the 13 carriers per square centimeter, theoretically expected 3.3 10 to the 14 per square centimeter, and I will explain in a moment why. So there is a factor of 10 discrepancy between transport and between what's expected, and I'll comment on that. That's an important element. The carriers, as I said, that make up this two-dimensional electron gas, there are electrons coming from the titanium orbitals in the T2G triplet manifold. So we have what we would call DXY orbitals, which lie parallel to the interface, and DXZ and DYZ orbitals, which lie perpendicular to the interface. Now, we heard, in fact, yesterday, a few things about transport, unusual transport, and I will give you some hints that this system, even though Isao mentioned the fact that it's not obvious that it's strongly correlated, but nevertheless, there are some things which are not so common. In the previous transparency, I showed, without mentioning it, but I showed gates. And you can actually backgate the system thanks to the very high dielectric constant. And so if you do, as was mentioned earlier this morning, you can apply a gate voltage between minus 300 volts and up to 300 volts. Now what you see is that in the very negative depleted regime of this 2DAG, you see that, in fact, KFL is on the order of 1. So the Joffe-Regel criterion is barely satisfied. And you see that as you increase the gate voltage, so you dope the system more and more, at 0 temperature, there comes a moment when you can enter a superconducting regime, and you see that there is a quantum critical point, Anderson insulator to superconductor transition at KFL equals to 4, which is what you would expect, because if, let's say, you take the H bar over E square criterion, then that's exactly what you would get in terms of single particle Joffre-Regel criterion. Okay, so you keep going, and then if the gate voltage is too high, then the system loses superconductivity. I mean, you cannot reach the point where you see a second quantum critical point where superconductivity dies down to 0. Now, at the top of this dome, between the normal and superconducting regimes, you see that, oh, you don't see, I'm sorry, but there should have been KFL equals to about 50. Okay, so let's. Yeah, I'll come to this point. Okay, so KFL equals to 1, so we are here. Okay, and you see that the sheet resistance as a function of temperature, here the temperature is quite low, doesn't seem to mind much. So in other words, it looks like even though the system should enter a strongly localized regime, that this does not show in the sheet resistance. Or, in other words, you can analyze the temperature dependence of the sheet resistance in terms of weak localization, and it gives you a very good fit to experiments. Now you can move on to this regime where you get KFL equals to 4, and you place yourself at a temperature which is about 5 times the maximum TC at the top of the dome, and you analyze the system, either the sheet resistance, either in temperature or in magnetic field. So you do magnetotransport. And what you see is that there's something very unusual that happens. Here, magnetotransport in this regime is consistent with what weak localization would tell you. So there is basically, as you crank up the magnetic field, the resistance of the system goes down. That's expected. But in this regime, that's the other way around. So in other words, you have anti-localization, and once again, you can analyze this anti-localization regime by looking at the magneto-resistance of the system. Of course, you include superconducting fluctuations, you include disorder fluctuations, everything you might think of, but anti-localization means that there is some spin orbit energy coming into play. Okay, so you can do transport measurements to see if indeed the vortex seem to play any significant role. Answer is that the region where they play a role is very close to TC. So there's no huge regime where you have these. Oops, I went the wrong direction. Okay, so now. As I said, in this regime, you have strong spin orbit. Now, this strong spin orbit is so strong that you find that the diffusion time associated with spin orbit processes decreases until it reaches the transport elastic time at around this gate voltage. And beyond that, it means that this guy is smaller than the elastic transport time. So that means that essentially spin orbit processes no longer are diffusive. Not only that, but the characteristic spin orbit energy that you can determine for the system becomes on the order of EF. EF is about 20 millieV. Maximum spin orbit energy is about 5 to 6 millieV.
So the temperature is much lower than EF.
Yeah, absolutely. But then what this means is that beyond this limit here, it means that essentially the system reconstructs its Fermi surface. Before that, spin orbit was just a diffusion process, so it did not affect the shape of the Fermi surface. Beyond this point, it does, and so the shape of the Fermi surface is affected by the presence of this spin orbit term. So that's quite unusual. Now, I would like to point out, because there were some interesting slides shown this morning by Professor Ye, on molybdenum disulfide with very similar phenomenology. Magnetotransport in this regime is no longer a function of the log of the field, but becomes linear in magnetic field. So it's anti-localized, but with a linear dependence, plus the fact that if you try to analyze the magnetoresistance at, let's say, 1.5 Kelvin, 5 times the maximum value of Tc here, you find very strong electron-electron interaction contributions. So it looks like in this regime, electron-electron interactions do become significant. Now, there is something more to the story. So I described what was going on. I would say, I said that as you change the gate voltage of the system, you go from what would be at zero temperature and insulating regime to something where the system develops superconductivity and so on. But there is more to it, because it was found by different measurements, squid magnetometry for the superconducting regime, torque measurements for the normal regime, transport measurements. It was found that there are magnetic signatures in this system. So this 2-deg sustains superconductivity, high spin orbit energy, and magnetism. Now, if you stop and think for a second, you'd say spin orbit and magnetism, that's odd. How do they, how can they be compatible with one another? Yeah, big, no, it's no problem except for energy scales, okay? So let's talk about energy scales. Superconductivity, 40 micro eV. Spin orbit is about, at the maximum, 5 millieV. Magnetism, 50 millieV.
Yeah, but it's just that it characterizes the magnetic state. But that's all. One is isotropic, and the other one just gives you an isotropy.
Oh, okay. Let's wait a few transparencies, and you'll see the interesting thing developing. So, okay, so let's go back to explaining where do these carriers come from and what is their nature. So what we do is we look at the structure of this system. I said that we had the substrate, STO, and the overlayer, which was LAO, lanthanum aluminate. If you look at the structure of STO, you see that there are layers. Each layer is charge neutral. You can count valence of the ions, so it gives 0 in total. But for lanthanum aluminate, we see that LAO, the LAO layer, carries a plus charge, and the ALO2 layer carries a minus charge. So we pile up plus, minus, plus, minus, plus, minus. So in effect, we construct a capacitor in this system with the plus plate close to the interface and the minus plate at the opposite end. When the electrostatic energy that's stored exceeds the band gap of STO, then there is some kind of, the band gap of STO, then there can be a Zener breakdown where charge is transferred from the surface of LAO to the interface. And let's see this a little bit more in a cartoon, just to understand what's going on. So here is DFT calculation showing ALO2, top layer. Here, LAO at the interface, or close to the interface, and STO on the bottom side, and TiO2 is the contact layer on the STO side at the interface. Negative plate, positive plate. So you see that this negative plate will pull every band's valence as well as conduction up. And conversely, plus V will push all the bands rigidly, if you believe that there is a rigid shift, down. And so you see the trend. Now, when the top valence band on ALO2 reaches the position of the Fermi level, then charge is transferred from here to the conduction band, which has moved down. And that's how you get through this, I would say, band bending kind of description, you get a gas, the 2-deg. Okay, now, the problem with, oh, not the problem, but one issue with this is, okay, so there is this mechanism. But this is quite controversial. There are people who are telling you that's not the mechanism, and there are good reasons to sort of question how operational this mechanism is. So, you know, one way of dealing with it is say, can I just take the surface of a non-polar material and just repeat what we just saw? And indeed, with the liquid gate, essentially, you can electrostatically dope the system, and indeed, how it was found, as mentioned by Professor Ye, then indeed for STO, when you apply liquid gate, you can turn the system into 2-deg. Okay, so that's good. Now, more recently, there was a big surprise. So STO, again, cleaved in high vacuum. Okay, so the cleaved surface of STO. So you look at it optically, and there's the Paris Metro, and you see that it's transparent. So essentially, that tells you that there are so few carriers in the system that it is an insulator. If you increased by doping the system with oxygen vacancies, say, then you turn it into a metal, which would show by these, the dark aspect of the same sample. Okay, very good. Now you shine UV light, the photoemission experiment, and what do you see? What do you see? You see bands, parabolic bands, and at the same time, you see a shift of the valence band. Okay? So that tells you that the system, the surface, is conducting. Now, what does, you see that if you have a little bit of experience with photoemission, you see that there are several bands. Let me just look at the time here. Okay. And indeed, if just qualitatively speaking, you say, let me assume that confinement is due to some kind of electric field which causes band bending, then semiconductor physics tells you it's very simple. You make some modeling of this 2-deg using a triangular weld potential, and then what you find is that the energy levels are quantized now, because if you have a surface and if you have an electric field which confines a gas to the interface, motion in the perpendicular direction to the interface is staggered, and you have 0-point energy which results. And this 0-point energy gives you these energy levels. So that's basically these successive consecutive bands. And there is more to it, because as I said, for STO, the T2G triplet consists of parallel orbitals, dxy, and perpendicular. And the perpendicular ones, they want to hop in the z direction, and of course, because of this confinement, they cannot. So their 0-point energy due to this confinement is much more severe than for the dxy orbitals. So what we see is that the lowest subbands consist of dxy orbitals, and the higher ones to dxz, dyz. And this is actually quite important. Now, if you compute the number of carriers in the system, seen in photoemission, it is on the order of 10 to the 14. As expected, in the polar catastrophe scenario, even though there is no polar catastrophe scenario because there's no LAO. Okay? And fine, and then the thickness of this gas is estimated to be anywhere between 1.6 to 3.2 nanometers. Okay, so this is confirmed. So you see not only the light bands, which I was showing you in the previous transparency in photoemission, but you also see the heavy bands, ellipses. Now, okay, very good. So this is an energy dispersion versus intensity of the light diagram. And what you see is, I know that those of you who are DMFT aficionados, you'd say, oh, here is a quasi-particle peak and a lower Hubbard band. Not so fast. Okay? Quasi-particle peak, indeed, these are the surface bands, absolutely. But this guy here is, in fact, an in-gap state at minus 1.3 eV. And this in-gap state can be connected to the presence of oxygen vacancies. And in fact, this pull down of the valence band is exactly in line with the appearance of this in-gap state. Now, this in-gap state, and I want to make a case for it, is quite universal. In other systems which display this surface 2-deg, like anatase, which also shows a 2-deg, you do see an in-gap state at minus 1.3 eV. Potassium tantalate, in-gap state at minus 1.3 eV. Last but not least, LaOSTO, in-gap state at minus 1.3 eV. So those people who say it is polar catastrophe, period, may be missing a few things. I'm not saying that this is, that polar catastrophe doesn't play a role, but I'm saying that's, that's far from being the end of the story. Now, as I was saying, there is something more to it, and Jairo was referring to it. So spin-RPES spectra experiments were performed more recently, and what they showed is that these two bands which I was showing previously, the parabolic bands, well, they are spin polarized. So this shows that there is something which you would associate with Rashba splitting with a lateral shift, delta Kf, of on the order of 0.1 angstrom to the minus 1. Okay, so this seems to suggest that these bands present Rashba-like features. Okay? Now what you do is you scan in energy. Okay? You go down in energy and you look at the bands, these two parabolic bands. What do you see? So if you're close to the Fermi energy, okay, two bands, and they're polarized, as I mentioned previously, Rashba. So you go down in energy, you still have two bands, and finally, 100 millieV below the top of the first one, then you see that the bottom one is here and only here. So that means that not only do you have Rashba, but in addition, you have some spin splitting of your bands. And that's where I'm saying, if we look at the energy scales, okay, we have to understand how that is compatible. So I will come to this point, but first I would say that oxygen vacancies, I don't know how far I'll go. I'll try to go as far as possible. Oxygen vacancies, they play a role in establishing this Rashba splitting, this Rashba texture, this Rashba polarization, if you like. How can that be? Of course, the first player in the story is breaking of inversion symmetry, and you'd say I have a field gradient at the interface, so I obviously will or may have Rashba. And indeed, you do, but it's a small effect. Now, what happens when you have oxygen vacancies is that if this vacancy does not move in its vicinity, you have a distortion of the structure, which allows a mixing of your orbitals. And if there is bulk spin orbit, and that's the case for bulk STO, 25 millieV, then you will get large Rajba contributions at some positions of the band structure of your system. Magnetism now. Okay, so magnetism, well, it can be intrinsic or extrinsic. Now, there were scenarios which were proposed in order to advocate an intrinsic mechanism. What does intrinsic mean? It means that at the surface of STO, or LAO-STO at the interface in this particular case, you have dxy electrons, and these dxy electrons are localized. How are they localized? Two possibilities. Disorder is one, but the other is MOT. Yeah, we have MOT in our system. And indeed, 3.3 10 to the 14, which is what polar catastrophe would tell you, corresponds to a quarter-filled band, and umklapp can make it so that the system creates a charge-ordered state. And then the next dxy orbitals in the other subbands will, through RKKY interaction, spin polarize the titanium, which are localized, the dxy titanium electrons that are localized at the interface or at the surface. Hund's rule is another proposed scenario which involves double exchange, but I obviously don't have time to go into that. Okay, so the other is oxygen vacancies, and indeed, in that case, it has been proposed that this could give rise to magnetism in the system. Now, as I said, we have to probe for the possibility of having both magnetism and Rajba textures. And what I'm saying is if you take into consideration a single band with the energy scales that I mentioned, that's not compatible. You will have either one or the other, but a tiny amount. Now, ARPES saw a very big signal for these textures. So that would not be consistent with that. However, as I said, a particular aspect of these titanium atoms is the fact that they have T2G orbitals and EG orbitals. And in whatever remaining time I have, I would like to try and show that magnetism is due to these EG orbitals, and the T2G orbitals contribute to the spin textures. So I don't know if I'll succeed, but okay, so how did we do this? Two ways. One is doing DFT calculations for slabs in the presence of oxygen vacancies, and the other is finite cluster analytical calculations. And I won't go into details, but I'll tell you what is the advantage or the interest of doing these cluster calculations. First of all, a single oxygen vacancy in this cluster, which means, in fact, a finite concentration of vacancies, doesn't do it because it doesn't show in-gap states, no 1.3 eV. Okay, for two of them, without looking at magnetic states, one does get in-gap states as expected, but their energy is too small as compared to what experiments suggest. So our quest was, can we recover the 1.3 eV peak? Where do the extra states come from, and how about the spin sector? So, okay, so we looked at configurations of die vacancies, which will give us better agreement with experiments, and our cluster calculation do exactly the same thing, However, there is a big advantage of doing a cluster calculation. You can introduce defects adiabatically. So in other words, all the perturbation that you have when you include a vacancy or divacancy in your system, you can mimic by just saying that the associated energies, they change, they increase from 0, no perturbation, to 1, full perturbation. And when you do this, let me just skip a few. When you do this, you see something quite surprising. So you see unperturbed state, vacancies, full vacancies in, and you see that now from the valence band, you see that these new states emerge. These are EG states, but also you have some T2G states. However, instead of coming from the conduction band, as the rigid shift model will tell you, it looks like they come from the valence band. So that's an unexpected result, but as I said, then the rest is confirmed, so let me skip, because I'm out of time. I realize, so I will try to see what's more essential. So DFT confirms this magnetism. Okay, let me just skip. Okay, here, just if I can have 2 minutes. Okay, so if we do DFT calculations, non-magnetic configurations, then we do recover the spin textures, so the Rashba effect, as soon as the situation is such that magnetism is allowed, by including a correlation U on the titanium atoms of 5 to 6 eV and a J term for 0.7 eV, magnetism becomes stable, and this magnetic state kills the Rashba spin textures. Okay, so what this says is that you can have cheese or dessert, but not both. Okay, so the question is, we do see both, so why? And this will be the end of what I want to say. The first possibility is that the surface of strontium titanate, as explored in experiments, has puddles. Some of them with, let's say, magnetic state or magnetic regions, and others non-magnetic regions that would be inhomogeneous. Inhomogeneous in that sense. The other possibility is that in terms of experiments, you can make sure that the surface of STO is cleanly terminated by TiO2, but in practice, you cannot control it to half a unit cell. So what you could have are mesas of one termination with mesas of the other. And in that case, indeed, you could have some coexistence of both textures and spin splitting. The other possibility, which is, I think, quite interesting, this has been referred to earlier in this session, in this workshop, is the fact that you have a case of orbital selectiveness. So some of the electrons want to be EG and the other T2G, and they can give you different types of states. But a last remark, which is, which echoes the situation that people think about in high TC, for instance, is the fact that due to this 0-point energy effect that I was mentioning, the dxz, dyz, and dxy bands, they cross. They shouldn't. At least in the bulk of STO, they don't. Truly, close to the gamma point. But here they do. So what that means is that due to spin-orbit effect, a Fermi surface consists of heavy, light, heavy, light, heavy, light, etc. So the area of the Fermi energy consists of states with different orbital character. And that is the final possibility. And with this, I thank you for your patience and attention.